Okay, Year 12s, this is going to be our video for exercise 5, which is about inverse functions, but specifically about inverse functions related to exponential and logarithmic graphs. So we've got two key skills that I've mentioned here. The first is being able to find inverses of exponential and log functions. So we've got an exponential, we're asked to find the inverse, it's going to be a logarithmic function. We've got a log function, we're asked to find the inverse, it's going to be exponential. And the second skill is just showing correct working when finding an inverse, and I've put this here to emphasise the importance of showing all our working if we want to get all our marks. So just remember that if I have log base a of a to the power of x, then what I get there is x. And one way to think about that is using our log law, that this power of the argument of the logarithm will become the constant multiplied out the front, and then log base a of a is always 1. Or you can simply think of it that a to the power of x, and then taking the logarithm of base a of that expression is an inverse. So raising x as making x the power of a, and then taking the logarithm of base a cancels each other out. I'm left with just x. And in the same way, a to the power of log base a of x, I'm also going to get x. But noting that for the first one, when I've got a to the power of x, x can be all the real numbers, because assuming that a is positive, which we are assuming, a to the power of x is always going to give me a positive result, regardless of whether x itself is positive or negative. So if x is negative, it just means I'm going to have a to the power of something on my denominator of the fraction. So I'm still going to have a positive number, and the logarithm can have any positive number as its argument. On the other hand, if I take log base a of x and then make that the power of a, then inside the argument of log base a of x, that argument can only be positive numbers, therefore x can only be positive real numbers. Okay, so we'll look at the first example. Find the inverse function of f such that the reals maps onto the reals for f of x equals 3 times e to the power of x plus 1, and I need to state the domain and range of the inverse. So the first thing I'm going to write down is let y equal 3e to the x plus 1, because there is no y given to me in the question, so I need to define it in order to then write swap x and y for inverse. So this is an important part of my working, which I must show. Then I actually do that, x equals 3e to the y plus 1, and now I'm going to use my algebra to rearrange this equation and make y the subject. So I've got x over 3 equals e to the power of y plus 1. Now I'm going to take the logarithm base e of both sides, and that gives me log base e of x over 3 equals y plus 1. And then I can rearrange that to get y equals log base e of x over 3 minus 1. Okay, so the inverse is going to be f neg 1 such that the real positives maps onto the reals. And it's got to be real positives, because inside the argument I can only have positive numbers. Dividing it by 3 has no effect on what x can or can't be. And f neg 1 of x equals log base e of x over 3 minus 1. And then I'm asked to also to state the domain and range of the inverse. So the domain I've already established is the positive reals, and the range is all the real numbers. Now, the range I can see easily because it's given to me in the question as the domain of the original function. So the domain and range are going to be swapped. But the domain of the inverse function I needed to work out. And there's a couple of ways of doing it. I can just think about what can go in here, what can go in the argument of my function, and it has to be a positive number, and work out how to make the argument of the logarithm positive. Or I can look at the original function, which is an exponential function that has been translated horizontally but not vertically. Therefore, the horizontal asymptote at y equals 0 will not change, which means I have a vertical asymptote at x equals 0 when I find the inverse. And that's why x equals 0 is the boundary. So it looks like this, 0, infinity, with curved brackets on each side. All right, example 2. I need to rewrite. So now I'm not looking for an inverse function, I'm just rewriting. Y equals 2 log base 10 of x minus 1 plus 1 with x as the subject. So I'm just going to take this step by step, subtract 1 from both sides. Y minus 1 equals log 2 log base 10 of x minus 1. Then divide both sides by 2. Y minus 1 over 2 equals log base 10 of x minus 1. Now I know I'm ready to change from logarithm to exponential when I've got a clear logarithmic expression with nothing added or subtracted or multiplied. So I started with my logarithm was multiplied by 2 and then 1 was added. Now I've rearranged it so I've just got a logarithm on its own and I'm ready to take 10 to the power of both sides. 10 to the power of y minus 1 over 2 equals x minus 1, which leads me to x equals 10 to the power of y minus 1 over 2 plus 1. And I'm done. Okay, my last example is rewrite p equals a times e to the power of kt with t as the subject. So here what I'm going to do is I'm simply going to, in the same way, I'm going to rearrange it until t is the subject. So first I'm going to divide both sides by a. P over a equals e to the power of kt. Then I'll take the log base e of both sides. Log base e of p over a equals kt. And now I'm going to divide both sides by k, giving me t equals 1 over k times log base e of p over a. Oops. And I'm done. Okay, that's exercise 5H. Just one video for this one.